Hello, everyone. So we are back for the second talk of the day, César Lozano Huerta, and he's talking about the effective cone of the moduli space of sheaves on the plane via minimal free resolutions. Please, César.
Right. Thank you for the invitation. It was a long name, and probably too technical. But before I get into the details of the talk, let me give you a puzzle. I cannot guarantee that it's not going to be terribly boring. So you can try to come up with a proof of the following fact. So suppose you have a plane curve, an irreducible plane curve of degree 7 with one node and no more singularities. And you place on it 12 general points. So it's not so difficult to prove that the points don't move. Points don't go. They are effective. They are an effective divisor, but they don't go anywhere in its linear system. That's what this equation says. So my goal with this puzzle will be: is it possible to specialize gamma so that these points move in its linear system? And something kind of funny happens, and I want to tell you what. So specialize, let me change the color to emphasize that this is, so pick gamma a little bit special so that it moves. Let me tell you how special. So if gamma is general, it does not determine a section of the tangent bundle of the plane. But sometimes you can specialize gamma just a little bit, so it determines uniquely a section of the tangent bundle. Let me be more specific. Pick gamma such that this H naught of the tangent bundle twisted by 2, this tangent bundle has 24 sections. And when you impose that those sections vanish along gamma, one of them survives. In other words, that gamma fully determines that section. Specialize gamma that way. So if you do that, then let me draw again the picture above. So here is C, right? And 1, 2, 3, 4, 1, 2, 3, 4. So here is gamma right there, 12 points on C. If you specialize gamma like that, then it turns out that it still doesn't move. Still 1. But here's the funny part. We have a specialized gamma so that here there is a section here. Let me call this section S, and observe that the second Chern class of this tangent bundle, this twisted by 2, is not 12, it's 13. And here we have a section that vanishes along 12 points. Therefore, the zero locus of S, in this case, is gamma union a uniquely determined P, uniquely determined by gamma, right? Which is the other zero point where the section vanishes. So if you go and place that node along P, exactly at P, it turns out that the gamma moves in its linear system. This is 2. And the puzzle asks for a proof of this. Why am I telling you this? I will use, it turns out that a proof of this fact already has a good chunk of the ideas we had to deal with in order to prove one of the theorems I will mention a little bit later. So
should that be gamma union P, César?
Yes, gamma union P, Jack.
Okay.
In the zero locus of the section, right?
But down where H naught is 2. Is this gamma union P?
Oh, and no, this is no. This is just gamma. Just the 12 points on this on C. And the P will be
if gamma is chosen such that the 13th point happens to be the node of the curve. Okay.
Exactly. If I don't care where the node is, even though gamma is picked so that it satisfies this, it still doesn't move. But now if I kind of choose the curve, kind of move the curve so that the node is at P, then the gamma moves on a pencil. And is that okay?
Yeah.
And so as I was saying, I will come back to this question, and I will use this computation to argue some sort of movable cone stuff. So okay, so that's the puzzle. The puzzle asks for a proof of this. And now now let me project the title of my talk, since I just jumped straight into a puzzle. There's the effective cone of the moduli space of sheaves on P2 via CCGs instead of writing minimal free resolutions. It is shorter that way, but it in my mind it means the same. So the goal of this talk is to bring two technologies together. One of them is Brill-Noether divisors, an interpolation developed by Isaac, Jack, and Matthew. And the other one will be minimal free resolutions of sheaves. And that's one thing, that's the goal, that these two technologies kind of talk to each other. And I should say that all this is joint work with Tim Ryan, who is a postdoc at Michigan, who will soon be on the job market, and a PhD student, the National University of Mexico, Manuel Leal. So, okay, so since I want two technologies to talk to one another, minimal free resolutions and interpolation and Brill-Noether divisors, let me start with minimal free resolutions, tell you something just to be on firm ground. So the ingredients of a minimal free resolution, we start with the polynomial ring in n+1 variables and a graded S module that we want to study, finitely generated, of course. And we want to, my understanding is that Hilbert wanted to understand these modules, was studying these modules, and he compared those modules to free modules, which are easier to understand. So this is basically the Hilbert CCG theorem that says that if you have a graded S module, then you have like that, then it has a finite graded free resolution. And by that, I mean that all these guys are free modules, which means basically copies of S. And then in that paper, was over 100 years old paper, he studied the Hilbert function, and when this Hilbert function became a polynomial, the Hilbert polynomial and the Hilbert CCG theorem and the Hilbert finite generation theorem also in that paper. And by comparing those modules against these free other modules in an exact sequence like that, which fails to be exact at n. And if we are considering one of those resolutions, then I haven't told you anything about the differentials. So if the differentials all, I will denote, here will be dl, here will be d1. The differentials go from a free module into another free module. And what that means is that I can understand this map as a matrix. And if that matrix has polynomial entries, always, I will call that resolution minimal. In other words, the domain of these differentials and the codomain are free modules. So I can talk about the basis of the domain. If the basis goes into a minimal set of generators of the image, then we'll call this, let's see, we'll call this resolution minimal. Let me label because it's not labeled. In other words, I need to understand these differentials as matrices with polynomial entries. Okay, so those are my minimal free resolutions. And let me give you an example. An example will be useful later on. So let me tell you something about 3 points on the plane. Okay, so if C is general, three general points, let me call this general, then the minimal free resolution looks like that. I need 3 quadrics, and the CCGs are of degree 3, and there are 2 of them. That's one resolution. If C, the 3 points are collinear, the resolution changes. And in this case, I have the line the 3 points lie on, plus the cubic. It's a complete intersection. And there is only one CCG of degree 4. Okay, so I want to emphasize that if you look at zero-dimensional schemes, zero-dimensional subschemes of P2 of length 3, any of them have a minimal free resolution whose numbers look like this. Of course, there are plenty of configuration of 3 points. So this brings me to the point I want to emphasize, that minimal free resolutions, minimal free resolutions, we mean 2 things. They consist of Betty diagrams. And a Betty diagram is the arrangement of the numbers above. Betty diagram plus a matrix, which is what lies in here. I can encode this arrangement of numbers in a Betty diagram slightly more compactly, writing it like that. So I have 1 plus 1 is 2, 3 quadrics, and 1 plus 2 is 3, 2 cubics. So I encode the information right here in this diagram. And I don't need to emphasize that this tells you anything about the map. So the minimal free resolution in this case will tell me the matrix. In this case, the matrix has polynomial entries of degree 1. Okay, so the minimal free resolution of an ideal consists of 2 things. The Betty diagram, which is just the numbers, tells me nothing about the map, and of course the map itself, which is a matrix with polynomial entries. All right, and actually this example, when it comes to points on P2, this example is not very misleading. So all the points, I can understand all the points on P2 with a minimal free resolution of this length, meaning a single matrix. And that is basically the content, of Hilbert Birch right here. And it says that if one takes a subscheme of dimension 0 and length n on P2, its minimal free resolution looks like my example above. It has only only length 1. So in other words, there is only one matrix kind of determining this subscheme. And of course there is, I can get generators for the ideal as the minors of this matrix. In this case, in my example, actually, this matrix with polynomials of degree 1 as entries, if you take the 3 minors, that accounts for this number 3 right here, which are the 3 generators. All right. A consequence of this theorem is that there are finitely many Betty diagrams. All right. So the conclusion, the moral of the story is, when it comes to understanding points on the plane via minimal free resolutions, I need to understand a matrix and finitely many of them, because there are finitely many diagrams, Betty diagrams. Okay, that was crash course on minimal free resolutions. Now let me tell you something about the Hilbert scheme. Something I didn't say at the beginning is that I will, during the talk, I will work with the Hilbert scheme, even though I will state the theorems in the generality that we think we have, which is for the moduli space of sheaves on the plane. So in this case, this is fancy notation for sheaves of rank 1, slope 0, and discriminant n. This is nothing but the Hilbert scheme of n points on the plane. It's irreducible, smooth, and of dimension, oops, something funny happened. And of dimension to n. Oh, I see. I'm sorry about the swinging. I was here, dimension 2n. And what that means, right? Because the Picard rank is 2, so I can allow myself to represent divisor classes on the plane like that. And now I can ask questions like Carolina did during her talk. So I can, if I represent divisor classes on the plane, what's the effective cone of this Hilbert scheme? Represent that effective cone on the plane. Well, people ask this question and fully answer it. That's work of Jack. And I will mention that in a little bit. But I can ask for finer information, which is the stable base locus decomposition. That will be a decomposition of this plane, like that, into chambers. What do I mean by this decomposition? If I take D, I will look at the stable base locus of D. And there is a theorem that says that this is locally constant. Locally constant. So what that means is that as D crosses the effective cone, there will be chambers in which the stable base locus remains the same. And I would like to describe those chambers. What's the information I can give you about these chambers? Well, one information is the base locus, and the other one is the ray, right? What's the class of the ray that bounds this chamber? So there is hope that I can I can finish this task in finitely many hours, in finite time, because these spaces are Mori, these moduli spaces of sheaves are Mori dream spaces. Which ensures that this decomposition will be finite. So I will ask for the stable base locus decomposition of this space. What is it? And now that I told you two things. I have minimal free resolutions on one side, and I have this decomposition that I know exists, the stable base locus decomposition, and I want me to tell you something about the relationship between these two things. And before I go on, let me show you some tables, some examples why such a question will make even sense. So I will stop sharing this screen. And now I want to use this because my handwriting gets out of hand. So 3 points, the minimal free resolutions of 3 points on the plane. I already told you, these are all the Betti diagrams there are on the left. And on the right, this is the stable base locus decomposition of the Hilbert scheme of 3 points. Here I am omitting one chamber, the chamber of delta, but it's always there. I will omit that chamber because it's always there. For 3 points is what I already told you. For 4 points, right? These are all the Betti diagrams there are for 4 points, solid schemes of length 4. And on the right-hand side, you have the stable base locus decomposition. It's a one-to-one correspondence. For 6 points, again, it's a one-to-one correspondence. Of course, 6 is too small of a number. So interesting things start happening very soon, and very soon is 7. 7, in this case, something kind of interesting is happening. So here I have on the right-hand side the stable base locus decomposition. I didn't tell you what my notation means, but the L4 means 4 collinear points, and the Q6 means 6 points which lie on a conic out of the 7. Here are 7 points on a conic, 7 coconic points. And on the left-hand side, you have the minimal free resolutions, all the Betti diagrams there are. However, for me to get the first wall, the Q6, which is the extremal divisor, I need to do something to the map. I need to study the map, which is kind of expected, that the Betti numbers don't tell you everything. So in my notation, if I am to follow the notation of my previous slide, here the matrix M here will be, the entries will be linear polynomials of degree 2, and degree 2. That will be the matrix. The ideal will be the minors, the 3 minors. That 3 is this 3. And of course, the degree 3 is the sum of these 2 plus 1. The 3 minors of this matrix. And what this table is telling you is that if you pick one of them, one of these linear polynomials, and make it 0, that subscheme will be here. So this pattern actually persists, that we have to, in order for us to describe the stable base locus decomposition, we need to deal with the maps as well, which is kind of, again, is expected. So let me erase this. So, okay, so let me pose this as a formal question. Is it possible to determine the stable base locus decomposition out of the minimal free resolutions, all of them, meaning the Betti diagrams and the maps? This question is, I find this question interesting because, of course, the two technologies are kind of talking to one another. And minimal free resolutions have been studied for a long time. They have been around for quite a few years, and they are very accessible nowadays. There's fast literature about them, and the computers can handle them more or less easily. Whereas on the other hand, the stable base locus decomposition is kind of a difficult object. In general, it tends to be difficult to very difficult to compute it. So having a dictionary will be useful. Okay, actually, it's interesting. This is the the equivalent of the same question Carolina asked 20 minutes ago about understanding the decomposition of the effective cone. I am asking exactly the same in this context. Okay, so that's the modulating problem. And let me tell you, the beginning of this story needs to start with the effective cone before going to the decomposition. And that's a theorem by Iset, Jack, and Matthew, 2016, I think, was published. And what they did in that paper is they computed the effective cone for us using interpolation and classification of sheaves, of stable sheaves. And an important part of their paper, or their proof, is that they have an open set, so that if you pick a general point on that open set, they go and find a bundle with these properties right here, minimum slope stable bundle, that is cohomologically orthogonal to that F. And once you do that, with that bundle B, they form the Vril-Noether divisor, and that they go ahead and prove that it is extremal. So, but a crucial part is finding the bundle and proving that it's cohomologically orthogonal to a general F. That's an important part of their proof. And let me emphasize that in the following slide. Their proof uses crucially that they find a bundle that is cohomologically orthogonal to a general F. And I underline in here that they prove that using a resolution. But this is not a minimal free resolution. This is a resolution in terms of vector bundles. And the vector bundles are, in many cases, are non-trivial. So this is the point where we started. If we are going to describe the effective cone using minimal free resolutions, we need a dictionary between this resolution of vector bundles and a resolution and a minimal free resolution and how they interact. So I will keep that resolution there because that's basically the main result that we have. If you have a sheaf in the moduli space of stable sheaves with character C, if it fits into the above resolution, into the CHW resolution, then that means that it's Gaeta minimal free resolution. Here, the Gaeta means that the Betti diagram is the most general one. So if that happens, if F fits into this resolution, then it has the most general Betti diagram. But then I need to tell you something about the map. And the map can be written in the following form, where B that appears, a factor, a block that appears in this matrix corresponds to the minimal free resolution of E. And the way I understand this theorem is that before we were just computing minimal free resolutions, you computed the Gaeta minimal free resolution, and you end up with a matrix like this. And we understood after this theorem that this matrix has redundancies. By writing this zero, I'm not making the sheaf more special. So this zero is precisely killing the redundancies. So this map still corresponds to a general sheaf. Then when you kill all the redundancies of the minimal free resolution, then you end up with a matrix of this type. And then a structure kind of shows up where this matrix is the minimal free resolution of a bundle that Iset and Jack and Matthew considered. Okay, so now let me go back to my example of 7 points and contrast the 2 points of views, because CHW is definitely more robust. I told you that the minimal free resolution, the most general Betti diagram is this, right? That's the Gaeta Betti diagram. The map in that minimal free resolution needs a 0. If you write a 0 here, then you enter the stable base, the extremal divisor. If you don't write, if that matrix is general, then it is general in the sense of Iset, Jack, and Matthew as well. And that's the description of the effective cone for us in terms of minimal free resolutions. If I am to follow the paper by Iset, Jack, and Matthew, then I will tell you that the general sheaf in this moduli space, the Hilbert scheme of 7 points, fits into this resolution. And with this resolution, you compute this exceptional bundle. And then the extremal divisor comes with this definition, with this description in terms of interpolation. By the way, I'm kind of going towards my example by replacing this bundle with a tangent bundle. But here, this is a lot more robust, because here I see immediately what's the slope of the effective cone of 7 points on the plane, whereas here we don't see that. Okay, so that's a contrast. Now we know that the general sheaf has a minimal free resolution that looks like this, where E comes from the CHW resolution with a 0 here, and then we can define these locus, define the sheaves where these A and B fail to be full rank. That locus many times has higher codimension, but sometimes has codimension 1. And when it does, then it expands the extremal divisor. And the takeaway of this corollary is that we can indeed describe the effective cone using minimal free resolutions for the cases where this loci has codimension 1. Okay, so let me go back to my original question. So is it possible to determine the stable base locus decomposition out of the minimal free resolution? Well, so far the answer is yes, for some cases. I just described for you the effective cone case. And so far we can understand the movable cone as well for some cases, for some ends, not for many ends. And of course it's pending the inner walls. That's the meaning of the question. But then, so let me tell you something about the movable cone case, which we thought it was interesting because that's exactly, we worked out the case where the CHW resolution is on the nose, the Gaeta minimal free resolution. Meaning we know the effective cone as they complement the next CCG loci.
I think something happened with César, that his connection fell.
Also give us the movable cone via interpolation. In other words, so in this case, this movable wall is also determined by minimal free resolutions. I'm not telling you how, but we can do it. We actually do. It involves quite a few computations, and but we computed the class also, so that it is not only the minimal, not only the base loci, but also the class. So, and I am finishing almost with this. So I want to tell you two things about this theorem. Is that the base locus of the movable class, of the extremal movable class, the base locus is given by a Betti diagram with generic map. And that Betti diagram and those maps via interpolation determine a class which happens to be the movable class. But now that we have some sort of understanding that we move from the most generic Betti diagram to the not so general Betti diagrams in this case, we can keep on going to the other minimal free resolutions. And that's what we did. And now if you give me one n, we can run this algorithm and compute basically, I can tell you candidates for the minimal free resolution. And the slide I'm showing you does that for 12 points. What I'm listing here is the J divisor. This is the divisor that Isaac, Jack, and Matthew described, and we can also describe as a CCG loci. And here are all the base locus that we were able to find using this algorithm and minimal free resolutions. And right here in the middle, what I'm listing are the bundles that we had to use, minimal free resolutions for the bundles we had to use in order to prove that these are the base loci. And if you see here is the minimal free resolution of the tangent bundle, the one on top. Let me actually make a note here. This is the tangent bundle twisted by 2. Right, and that gives us this J, and then to prove that this is the movable class, to prove that this is actually the bound of the movable cone, we have to come up with moving curves. We have to how do I do this?
Sorry, Cesar, you have maybe a couple of minutes, 1 minute to conclude.
This is the last slide. And actually this is the end of it. If so this curve, to prove that this is the movable class, is the curve I told you at the beginning. So we need to kind of allocate the node, and that 7, the degree 7 of the curve is exactly this 7 down here. And anyway, that we had to come up with curves so that proving all these decomposition. And here are the faces involved in this story. I couldn't find a picture of Matthew. Well, thank you.